Hello everyone, welcome back to the channel. If you caught our last episode, you'll remember we dived into the world of grayscale images and played around with some Python tricks to manipulate them. Today we are turning up the color. We are going to explore how colored images work and show you how to handle them using Python. Get ready to add some vibrancy to your coding skills. Let's jump right in. Alright, before we dive into the colorful world of image processing, let's make sure our workspace is ready to go. If you have been following along, you should already have a virtual environment set up. Let's activate it now to keep our workspace clean and organized. Just follow along with these steps. Great! Let's start by setting up our environment with the necessary libraries. Today we are going to need several packages to work with colored images effectively. Here's how we import them. We are bringing in matplotlib for image display, numpy for numerical operations, and skimage for image processing tasks. Also, orderDict will help us keep our data organized. Now let's bring back some handy functions from our previous episodes. We have a function for summarizing numerical data about our images and another to display images neatly in our Python environment. These functions are essential tools in our toolkit, helping us explore and understand the data properties of our images and visually confirming our results as we go. Now let's dive into handling colored images. We will start by loading our image using scikit-image. Here's how we do it. Note that this time I didn't include the sgray=true argument. By skipping this, we ensure that the image retains its color information, allowing us to work with a full color image. When we dealt with grayscale images, we were working with a two-dimensional numerical array where each value represented the intensity of the white color. With colored images, the structure is a bit more complex. Let's inspect what we have this time. Executing these lines will reveal the type of the image object and the dimensions of our image array. Unlike the grayscale images which had just two dimensions, height and width, colored images typically have three dimensions, the height, width and the third dimension for color channels. This third dimension represents the color components, typically red, green and blue, RGB, allowing for a vivid representation of the image in color. Let's delve a little deeper into how RGB color representation really works and what makes it so crucial in digital color imaging. As we noted, colored images are represented as three-dimensional arrays where each pixel is defined by three values, red, green and blue. Each of these values can range from 0 to 255, indicating how much of each color the pixel contains. To see this in action, let's play around with some color combinations to better understand how RGB values affect the colors we see. We will start with pure red. In this case, the intensity of red channel is at its maximum, 255, and both green and blue are at 0, which results in a pure red color. Let's experiment with more colors. We can get pure green, pure blue. Now let's mix some colors. And in case if we mix full red and blue, we will get magenta. Finally, mixing all colors with maximum intensity results in white color, and the absence of all colors gives us black. This exploration not only helps in understanding the basic concept of color mixing in RGB, but also provides a visual insight into how different colors are formed. Now let's break down what's happening when we split the image into its individual red, green and blue components and then visualize each one. This method is an excellent way to understand the contribution of each color channel to the overall image. Here is a breakdown of each step. We start by creating current image, an image array filled with zeros, which has the same dimensions as our original image. This effectively sets up a blank canvas. Then we use array indexing to replace one of the color layers in our current image with the corresponding channel from the original image. This is done sequentially for red, green and blue channels using the loop index I. This way only the channel being processed will have non-zero values and the other two remain black. The next step is visualizing channels separately. Each modified image, which now highlights one of the RGB components, is then displayed in a subplot. We disable the axis to keep the focus solely on the visual content. The next step is saving. We save each individual channel as a separate image by using the IO-im-save method. And at the end we setting up the background. The figure's background is set to black to enhance the contrast, making the colors pop out more vividly. This visualization helps us see how much red, green or blue is present in different parts of the image. It's a powerful way about image composition and the role of color channels in digital imaging. Now let's check how can we perform image conversion to grayscale. Converting a color image to grayscale is a crucial step in many image processing applications. Let's explore two common methods to achieve this, each reflecting a different aspect of how images are perceived and processed. First, the straightforward approach is to average the RGB values for each pixel. This method treats each color equally, which doesn't align perfectly with human visual perception but provides a basic approach. Here we calculate the average across the three color channels for each pixel, which simplifies our colored image into a single grayscale intensity map. However, because the human eye perceives colors with varying sensitivity, more sensitive to green, less to blue, and moderately to red, the grayscale conversion often uses specific weights for each color to mimic this sensitivity. This formula is designed to reflect the human eye's differing sensitivity to various colors, providing a more perceptually accurate grayscale image. To implement this, we will use the RGB to gray function from the scikit image package, which automatically applies these weights. This function converts our RGB image to grayscale by applying the aforementioned weights, effectively mimicking how our eyes perceive color brightness. Now let's compare the summary statistics for both grayscale images to understand how the results differ. This print will show the statistical distribution of the pixel values for each method. This comparison will highlight how the perceptual weighting method often results in a grayscale image that might appear more natural to human observers. By examining these results, we can see that two approaches yield different outcomes, with the perceptually weighted grayscale often providing a more balanced and realistic representation of the original color image. Now let's check out alternative color models and explore their unique characteristics and applications. Understanding these different models is crucial for handling a variety of tasks in image processing and digital media. The first model is called CMYK, which stands for cyan, magenta, yellow and black. CMYK is fundamentally different from RGB as it's a subtractive color model used primarily in color printing. This model operates on the principle that colors are subtracted from natural white light into pigments or inks. These pigments are cyan, magenta, yellow and black. Here's the basic visual to help understand CMYK. The next color model that I want to cover today is the HSV, which stands for hue saturation value. HSV represents color in a way that's often more intuitive than RGB, particularly for tasks involving color adjustments or any processing that requires working with color in a more conceptual way. Hue indicates the type of color spectrum from red, green, blue, etc. Saturation describes the intensity of the color from pure color to gray. Value or brightness indicates the brightness of the color. Visualization tools in image editing software often utilize HSV because it aligns more closely with human understanding of color. And the last color space that I want to cover today is a lab. The lab color space is quite distinct because it was designed to approximate human vision. It's intended to be perceptually uniform, where a given change in a color value looks about the same across the spectrum. And this is a three-dimensional space where The first axis is called L star and it stands for lightness. The range for this axis varies from 0 to 100, and the two next axes are A star and B star, range from -128 to 127, representing green to red and blue to yellow respectively. Lab color space is particularly useful in scenarios where an exact color match is crucial, such as in textile, manufacturing, and brand color consistency. To illustrate the lab color space, let's create a visual representation using a 3D scatter plot with plotly. This visual helps to see how lab components interact to form different colors. So in the beginning we need to set up the color space coordinate. So in this snippet we import necessary libraries, plotly graph objects for plotting, and skimage_color for color space conversions. And dot is a variable defines how many points will be on each axis along A star and B star per slice of L star. Next we have LAB arrays. L is an array of linearly spaced numbers between 0 and 100, creating 5 slices of lightness values. These values 0, 25, 50, 75 and 100 represents different levels of lightness in the lab color model. A and B are arrays of linearly spaced numbers from -128 to 127. They represent the range of values for the A star, green to red, and B star, blue to yellow axis, respectively. Next, we creating a mesh grid by using np.meshgrid, and it's used to create a 3D grid where each point XYZ corresponds to a combination of LAB values. This mesh grid effectively lays out the entire lab color space in a structured 3D array format. Next, flatten is used to convert the 3D arrays into 1D arrays. This transformation is necessary to handle the data more easily in subsequent plotting and color conversion steps. It aligns all the points into a single list where each point position LAB corresponds across X, Y, and Z. This code uses plotly to create a 3D scatter plot. Each point in the scatter plot represents a color in the lab's color space, positioned according to its L, A, and B values. The layout is configured to label the axis and set the title. The aspect mode set to cube ensures that the scale is equal in all dimensions, providing a true spatial representation. Next, we want to use npd stack to stack the arrays along a third dimension, and reshape is used to create a two-dimensional array where each row has 3 columns. Next, we use color.lab to RGB, and we use it for converting lab values to RGB values. This step is crucial as it maps the abstract lab color values to visible colors on your screen. Now let's use coloring for our points. Each point in the scatter plot is now colored according to the corresponding RGB values derived from the lab values. And the final visualization showed the lab color space with accurate color representations, allowing for visual understanding of how colors vary with changes in L, A, and B values. This comprehensive approach not only visualizes the lab space, but does. In our next episode, we will delve into practical applications of these color transformations and explore how they can simplify complex image processing tasks. You can experiment with converting images using different color spaces and observe the impacts on your results. If you are curious, try loading an image with OpenCV and discover the default color space it uses. It's a great way to deepen your understanding of how different libraries handle color differently. Don't forget to join our Telegram channel for more tips, tricks, and discussions on machine learning and data science. The link will be in the pinned comment. Take care, my friend. See you next time.